Hello and welcome. This is the first discussion section of CSE 142 in summer session 2, 2023. As you may know, the discussion section is both in person, live streamed through Zoom, and also recorded. But right now I'm sitting in front of my computer at my desk at home, and that's because I forgot to record the discussion section when we're doing it in person. We didn't remember it until it's already halfway through. So I'm gonna just redo everything in a more organized way, and then I'll publish this recording to YouTube. The agenda for today is just all about assignment 1. So I'll guide you through the process of setting up the development environment using Jupyter Notebook, and also show you some LaTeX syntax, and also probably like the submission through Gridskope. I'll go through the whole flow of preparing and succeeding in the homework. So the assignment 1 can be found on the course website. And once you click on it, you'll be prompted to the GitHub Classroom to accept the assignment. I already did it. So I'm just gonna go to my GitHub and find the repo, right? This is a repo I just created by accepting that assignment. And essentially what we need to do first is we will clone the repo to our to the machine of at Jupyter Lab, and over there we can do the development, right? So this is Jupyter Lab. The link can be found at the GitHub page. And let me first open a terminal. And okay, so I just got a clean copy of the terminal, right? I don't have any files other than my personal file. So I'll go through the whole process. Since this is recorded, I'll do it a little bit slower. And if I've already done it, or if you know how to do it from 142L, feel free to skip this part until I think 10-20 minutes later, where I will cover the 3 questions in the assignment. All right, so I'll do it a bit slowly so that those people who are watching the recording can follow this. So what we need to do is we need to clone the repo. And to do that, we need to create a public-private key pair and then clone the repo through SSH. This is a recommended way. You can also do it through HTTPS with tokens. The instruction can be found online. Just Google GitHub authentication token HTTPS. There are a bunch of tutorials, but we're going to do it through SSH. And the way to do it is on the Jupyter Notebook. We first need to create a public-private key and then copy the public key to GitHub. And the command here is sh-keygen. Right, I'm just pressing enter, enter, enter. And now it has just created a new set of keys at this directory. So if I do an ls-l, you will see there's nothing ls-la. There's a hidden directory called .ssh, right? And inside the .ssh, there are a couple of files. 2 important ones, ID_RSA, that is a private key. And then this pub version is a public key. .ssh/ID_RSA .pub. And what we need to do is just to copy the whole file, the public key, to the GitHub. It's under my profile, settings, SSH, and GPG keys. I'm going to create a new SSH key. You can give it some arbitrary title, and then just paste the key over here. Right, adding the key, and it's all set. And once I've done it, I can go back to my repo and click on code, copy the SSH version of the address, and then I will go back to Jupyter Lab. In the terminal, I'll do git clone and then paste the link over here. Right, it's gonna automatically look for the private key in the SSH folder and do authentication. And now I have the project set up on the Jupyter machine. So I'm gonna go to this folder. And as you can see, this is a terminal, and on the left, this is the file navigator. If I just do a refresh, or it automatically refreshes every once in a while. This is the folder I'm looking at, the assignment 1. All right, and then you can double click on the assignment, and then it will pop up this very nice looking editor. This is a place where you can see the homework questions and also type your answers. All right. So there's 3 questions in the homework. The first question is we give you a program in C. We also give you the compiled x86 code. And we ask you to analyze the number of dynamic instructions, the execution time, and the speed up under various conditions. The third question, I'm going to skip through 2 for now. The third question is very similar to question 1, except that, we're dealing with floating point number, and we have, of course, some different x86 codes. And again, we ask you for the execution time and some, floating point operation counting. Question 2 is dealing with multiprocessor. In this question, we give you, we assume that there's a program that requires 100 seconds to run, and we ask you to speed up under various multiprocessor settings with some additional penalty or overhead. So I'll go through these questions one by one in one moment. All right. And before I do it, let me just finish the logistic. So before I do the questions, make sure to put your name and PID over here. And what I found is that there's, right now I'm using Safari, and there's a lot of compatibility issues with Safari where things do not refresh or they just get stuck. I would recommend you to use another browser like Chrome, but Safari will work if you just zoom in and zoom out once, right? And like essentially forcing it to refresh. It's not an elegant solution, but it will work, and I don't want to, I just love Safari so much, and I don't want to change. All right. So I think, in addition to that, once you have done with the homework, you just go to File, and then export the notebook as a PDF. And this will generate a PDF compiled version of the answers and of your answers, and then you can upload the PDF to Gradescope. And on Gradescope, you can select the questions by page, so that we can easily reach your question for grading. So that's pretty much everything about the logistics. I think the next part of the discussion section is just to cover these 3 questions, right? I'll try to point out some important stuff to keep in mind, and also make some clarifications. All right, so coming back to question 1. Question 1, we give you a relatively simple C code, and this code has a loop, right? It's going to iterate I from 0 to size -1. And in each iteration, we are reading from AI and BI, add them together, and then store the result back to BI. And this is a corresponding x86 code. So the way I look at it is, they're running like 3 parts. This part, the one before L3 block, this is essentially all the setup work, where we, prepare the variables, prepare the integer, the int I, the loop tracking variable, and also just setting up the environment. And then L3 until the jump not equal is the main loop. This corresponds to the main operation in the C code over here, right? And this loop will be executed again and again, depending on the current I value and also the size variable from the inputs. And finally, once I becomes size, then I will quit the loop and then just return from the function, right? So 3 parts. The preceding part setting up the loop and the actual loop body, and also the finishing part return from the function. All right. So one question I got during the discussion section is that what is a static instruction and what is a dynamic instruction? Okay, so right now what we're looking at here, this is the x86 code, and there are 2 ways you can count. You can count it statically or dynamically. The number of static instruction corresponds to the number of lines in your code, or the number of instructions in the code, right? And the way I typically do counting is that I will ignore all these instructions starting with a dot sign. Those are not real instructions. Those are more like flags, pointing to different locations so that we can do the jump. But the real instructions are, like this: and BR64, test L, JLE, jump less than equal, XOR, etc. Right. So really there are like 1, 2, 3, 4, 5 instructions over here, 6 instructions in the loop, and 1 instruction afterwards. So 5 plus 6 plus 1, 12 instructions in total. That is for the static count. As you can see, when we're doing static counting, we're not considering, you know, any of the runtime condition. We just look at the code counting the number of lines. And another way to count is do dynamic counting, right? To count the number of dynamic instructions. And to do that, we need essentially to run the code either in your brain or in a real machine or in some, like, you know, emulation environment. And essentially we'll plug in some variable numbers. Like over here, we assume that size equals 1 million. And then we're just going to follow the program line by line and count, actually, given that runtime environment, given that input variable, how many number of lines will the program actually run to finish the execution. So essentially, let's say suppose, you know, the variable is set to 1 million. So we know the else3 loop will run for 1 million times, right? So before the loop, we're still going to execute each of these lines just once, right? And then we enter the main loop. And for these 6 instructions, we're going to execute them 1 million times. And then after the loop, you know, when we finally return from the loop, we're going to, you know, also execute the return instruction for the function, right? So that's, you know, how we do dynamic counting based on some runtime variable value and actually tracing the execution path. And, you know, when we're doing dynamic counting, each line of the instruction can be executed multiple times, right? Particularly when we have drums and branches, right? That take us, you know, from this line back to a previous line. So, you know, just do the dynamic counting, you know, count the number of dynamic instructions, and that will be part 1A. So part 1B is a quite typical execution time question. So as you remember, this is the execution time formula. And this formula, the execution time is the product of IC, the instruction count, and cycles per instruction. So the product of these two terms will be the total cycle count. And then multiply that by cycle time, you get the total time, right? The total execution time. And in this question, we already tell you that the processor's frequency is 3 gigahertz, right? And then we can derive the cycle time quite easily. That's just the reciprocal of the frequency, right? So we know 1 gigahertz is 1 nanosecond of cycle time. So 3 gigahertz is 1/3 of a nanosecond of cycle time, right? 1/3 of a nanosecond, that's the cycle time. The instruction count, well, that should come from part 1A, right? The dynamic instructions are just counted. And the cycle per instruction is the thing that you need to figure out based on the question write-up, right? So as you can see, we're spending most of the time in the loop. And when it comes to computing the average CPI, particularly we just ask you to estimate the total execution time, you can just compute the CPI based on the main loop body, right? This is going to be the dominating part. And all the other instructions before and afterwards, they're going to be negligible once you execute the loop for so many times, right? So in this, among these 6 instructions, we have move L instruction that takes 5 cycles. So the first instruction takes 5 cycles. The second instruction, add L, takes 6 cycles. The branch instruction, that is a jump instruction over here, it takes 3 cycles, and all the remaining 3 instructions, they will take 1 cycles, right? And I hope you still remember the formula for average CPI. So in general, right, I'm just presenting an arbitrary example. It's not for this particular question. Suppose I have 20% of instructions taking 4 cycles, and then another 40% taking 5 cycles, and another 40% of the remaining instructions taking 1 cycle. And the way we compute average CPI is by just taking the weighted average of all those numbers. So 20% of the instructions takes 4 cycles, 40% takes 5 cycles, and the remaining 40% takes 1 cycle. This will be the average CPI. All right, and then once you got the average CPI from this kind of weighted average computation, and also the cycle time by taking the multiplicative inverse of the frequency, the instruction count from 1A, you can compute this, the total execution time. All right. So in section 1, in the part 1C, we're just making a modification to the processor. So as you remember, so in the instruction, in this set of instructions, these two instructions, move L and add L, are taking a lot of time. They're taking, 6 cycles and 5 cycles respectively. And also, they also dominate the cycle time. And the idea here is that to break each of these instructions into 2 instructions, so that we'll have a different CPI number, and also we'll have a different cycle time. So instead of having 6 instructions, the new architecture will have 6 plus 2, that is 8 instructions. Right, and again, we tell you the number of cycles taken by each instruction. You can compute the average CPI and then use this formula to compute the execution time. Part 1D, once you get part 1B and part 1C under control, I'm doing this trick of zooming in and out to refresh the page. This buggy Safari. Once you have computed the execution time of 2 machines, then you can compute the speed up, right? As you remember from the lecture, there's only one definitive formula for speed up. That is, speed up equals execution time, the old machine, or the one before the change, divided by the execution time of the new machine. Right, this is the speed up formula. And in this case, the old machine is your 1B, the new machine is your 1C. You just do a division between those 2 numbers, you'll get the speed up. Right. So since I'm already here, let me spend like maybe half a minute explaining some of the LaTeX syntax. So in our Markdown editor, if you put something between a single dollar sign, then it will be compiled as a LaTeX line, right? It will transform into this very nice looking arithmetic format. If you put it in under $2 signs, it's also going to do the conversion, but now it's going to center the formula. And also, if you have some other text before it, like my solution is this one, the LaTeX formula will go into a new line. Whereas if you use a single dollar sign, the formula will be placed in line, right? Depending on what you want, you may want to use both syntax. All right, and also this underscore is to create a subscript. And the other thing that I use quite commonly is the frac, right? This will create a fractional number like 4/5. As you can see, it becomes 4/5. All right, and in this case, I'm gonna break the line so that it's sit at 2 different lines. 4/5. And you can also use like nested fractional numbers. So if you say 1 divided by 1 minus p plus another fractional number, maybe p divided by r, you can also do it. All right. So some very basic LaTeX syntax and also how to use them in the Markdown environment. So as I mentioned earlier, question 3 is more relevant to question 1. So I'm gonna go through that question first before coming back to question 2. All right, so in question 3, you see the C program looks very similar to the program in part A, in question 1. The only difference is that instead of having integer, as in question 1, now we're dealing with floating point numbers. All right, and of course that translates to a slightly different looking assembly code in x86. All right. And basically what this code does is, so before the loop, it's just setting up those variables. And then in the main loop, we're first reading one of the variables. I think we're reading the BI first, and then we add it with AI. And then we store the result back into BI. We increment the index I, and then we compare the I with the bound variable, the size. And then we'll decide whether we jump back to the beginning of the loop to execute it again, or we exit the loop and then return from the function, right? The thing is, I know the syntax is very complex, and maybe we do not expect you to be able to convert the C program to assembly. what, I think it will be very helpful if you can just, compare the two parts, the C program and the x86 code, and then try to build a correspondence, right? That, just roughly understanding the flow of the program. That would be very useful for solving these questions and also, for your own understanding. All right. So 3A is very similar to, the other execution time question. We'll give you the frequency. You should be able to count the number of instructions from the program, from this x86 code, counting the number of dynamic instructions, and also compute the average CPI based on these parameters. All right. And question 3B, what's the gigafloating point operations per second? The name is pretty self-explanatory. So it's counting number of floating point operations, convert the unit to giga, that's 10 to the power of 9, and then divided by the execution time, right? So you got the execution time from part 3A. And the next thing to do is to count the number of floating point operations in the code. So actually in this code, the only floating point operation is add SS. Right. Add SS is, when we take one floating point number and another floating point number, we add them together and the result is also a floating point number. This is a floating point operation. Move SS, this is more of a memory operation. We go to the memory, we read the value, and we put the result, this floating point number, in a floating point register, but it's not really doing any operation with floating point. Right. So we only consider the add SS as a real floating point operation for part 3B. So again, you can assume that size is 1 million, and then you count how many times do we execute the add SS. That will be the total number of floating point operations. Then you convert the unit to giga and divide that by the total execution time. Right. So I guess we haven't seen the formula for this in lecture. Maybe we'll see it next time. Maybe this term is quite, it's, the meaning is pretty obvious by just looking at the definition. But you get the point. Not the total number of floating point operations divided by the total execution time. All right. So those are the 3 questions. Let me think if there's any questions that people asked during the live discussion section, and if I should bring them to your attention as well. Nothing I can remember for question 1. For question 2, yes. So yeah, I haven't covered question 2. So let me do that first. So question 2 is telling you there's a program that requires 100 seconds, right? So in line with what we have seen from the lecture, I'll draw a box for the original program. So suppose this is a total workload of the original program, which is 100 seconds, right? This is for one processor. One processor. All right. And what we're doing with 2 processors is that we assume that the whole program can be perfectly parallelized. So this 100 seconds will be divided into 2 smaller 50-second blocks. You know that drawing with a mouse is very difficult for Zoom. Oh my God. All right. So the whole 100 seconds of workload is divided into 2 parts, and then they're distributed evenly across 2 processors. But on top of that, we also tell you that each processor requires an additional 4 seconds of overhead. What we mean by that is, in addition to the 50 seconds, we also need to spend an extra 4 seconds on each processor to account for the overhead. Right, the overhead could come from multiple parts, like maybe, the 2 processes need to communicate each other. They need to synchronize some data from memory, and that causes some additional latency. Or just when we're doing the task assignment, it's going to take some time, right? It's going to take some efforts to break up the work and then put them on 2 processors. So for various reasons, there will be overheads And the way we represent this overhead is as some additional, an additional part on each processor. And by the way, I just want to point out that, the overhead over here is a little bit from what we discussed in lecture for the parallelizable and non-parallelizable part of the program. So here we assume that the whole program is parallelizable, and the overhead is some, extra penalty that comes later on top of, the workload that have been perfectly splitted. So this 4 seconds is not part of the original workload. It's, just appears freshly when we do the multi-processor design, right? So, it's not like 100 seconds comes and 4 seconds together is the original workload. No. The original workload is 100 seconds, and then we perfectly parallelize it, and then we add additional 4 seconds of penalty to each core, right? Because of this subtle difference, let me turn off my annotator. And because of this subtle difference, clear all drawings, then you may not be able to directly use the speed up formula, right? So the speed up formula is just showing the basic idea. We have the non-parallelizable part represented by 1 minus f, and also the parallelizable part represented by f, and then divide the parallelizable part by the number of processors. But, in this case, you need to have some additional term to account for the additional 4 seconds of overhead. You can probably adapt this formula, right, by, considering the additional overheads, like additional 4 seconds on top of the 100 seconds of the original workload. Or, you can compute the speed up using the standard formula, ET old divided by ET new. That always works. All right, and you can also, solve this question using both the standard division-based formula and also this Amdahl's law. You should get the same number, and you can use that to double-check your solution. All right. I think that's all I want to cover about the assignment. All right, and of course, if you have any questions, feel free to post it to Piazza. I'll monitor it every once in a while and try to solve the question as soon as possible. And we actually have another question. A student raised a question about the quiz, the performance quiz that was due last time. So maybe let me also bring it up in case you're interested. So the question is about question 2. Right, we give you the execution time formula, and we give you a bunch of numbers, and we ask you to figure out the missing number, right? So for this kind of question, the first thing you need to do is to identify what all these numbers mean, right? And convert them into the corresponding variable. Is it like IC or CPI or CT or ET, etc. So let's start with the Pentium 4 processor. So this processor has a 2 gigahertz frequency. And with the 2 gigahertz frequency, the cycle time will be 1 divided by 2 gigahertz. That's 0.5 nanoseconds. And then we also have 2 seconds of execution time. We also tell you that the CPI is 2.0. So among the 4 variables, we already give you 3. We give you ET, we give you CPI, we give you CT. That should be straightforward to figure out the IC, right? And the IC will remain the same between the 2 processors. So for Pentium 3 processor, you will derive IC from the Pentium 4 calculation. We give you the frequency, so you can derive the cycle time. We also give you the total execution time. So, again, you already have 3 variables out of the 4. Figure out the last one should be straightforward. All right. So that's the question about quiz that we received during the live discussion section. Let me see if there's anything else I want to cover. So maybe a little bit about navigation on the website. So as you know, we use the same Zoom link for lecture and discussion section. The discussion section happens at Pepper Canyon Hall, which is a very beautiful classroom. This is a pretty new classroom with all the fancy technology. Even though I still couldn't get the classroom camera to work, it's just showing me, the kind of noisy interface as you see from an old TV. Maybe I'll try to figure it out next time. I have office hours every Tuesday and Thursday before the lecture. So tomorrow before the lecture, I have 2 hours of office hour, and the link can be found on the course calendar. And all the important materials over here, right? We have the lecture slide, the preview. This will be released before the lecture, and also the updated one after the lecture. The assignment is over here. The reading quiz, the link for Canvas can also be found over here. All right. And then this is another important reference material, the x86 ISA introduction. So over here, you will see some explanation about, what each instruction means. Although, you don't spend too much time try to, dig through all the little details of everything. Have a rough understanding is good enough. And if you're interested, of course, you can spend more time just studying this ISA. All right. And as you can see, this is a 5-week class, and so everything is moving very fast. We have a lecture every day. And we released the assignment today. It's going to do in just a few days. So keep in mind, I think the first assignment is due on the 13th. I think that's Sunday probably, right? But please double check. All right, so I think that's everything I want to cover. I'll probably just hang around for another minute to see if I missed anything, right? Or if there's any other questions that people ask during the live session. And other than that, have a wonderful day and good luck with the assignment and good luck with the course. I think the course is very, very engaging. I hope you enjoyed it. I enjoyed it a lot, actually. I think, professor is very passionate. All right, so I'll just look around and I'll stop the recording in a moment.